last part of this tutorial.
In this lecture, I will talk about lower bounds for general extended formulations, and in particular, the lower bounds that I'll talk about are some reductions from so if you take a Shirley-Adams gap for a CSP, or let's say max cut or a CSP, you get a LP extended formulation lower bound. And if you take a sum of squares gap instance, you use that to construct an SDP extended formulation lower bound. And this is what we're trying to do now. But before we talk about extended formulations directly, let's look at something different, something seemingly not very directly related, but it's an interesting question. So let's just look at it, and we'll use this in the proof later. And so the idea would be that I may not be able to get through all the technical details of the proof, and maybe all of them are not important. So I'll try to get to the main conceptual details of the proof and the main ideas in the. But let's look at it. So let's directly look at one question here. So imagine you have a probability distribution f on the hypercube. Okay, you have a probability distribution on the hypercube, and this probability distribution is, I've normalized it as a density. So expectation of f is 1. So if it was the uniform distribution, it would be 1 everywhere. But it's not the uniform distribution. It's non-uniform, so it's higher at some places, lower at some places. We will bound the infinity norm of f by 2 to the t. Okay, think of t as a small number. Okay, and what you also have is you have a family of tests. Like think of these as a statistical test, or these just you can think of this as just as functions, for instance, d1 through dn over the hypercube, and your goal is to sort of construct an approximation for f. Against these tests. Okay. So what do I mean? You want an approximator f tilde. Make sure I have the right notation. Okay. Yeah. So we want an approximator f tilde. So in what sense is it an approximator? If you take any of the test, if you take a d, di, and if you take inner product with di, that's close to what it would be with the original function. So f tilde is an approximation for f, in the sense that on all these tests, the value of the function or the value of the test is within a plus or minus eta of the actual value. And of course, you would want f tilde to be also a density, right? You would want f tilde to be a density. And of course, we already had f at hand. Why do we want f tilde? We want f tilde because hopefully f tilde is simpler than f. F tilde is something we understand. Like for instance, f tilde could be a junta. F tilde is hopefully simpler. So it could be simpler in various ways. It could be a junta, it could be a low degree function, right? And it could be anything, but essentially we want a simpler object f tilde that we want to work with, which is as good as f with respect to these tests. Okay, that's the goal. Okay, so it's a very natural question. And so a priori, for me at least, it was a revelation that a priori you would think that there's no good approximation, because I'm just starting with an arbitrary function f. Okay, how good can what approximation can I get which is better than f, because it's just an arbitrary function f. But one fact which sort of is very revealing to me is that this is a recurring fact in it's like a meta observation, I guess, is that if you want trying to approximate something, the complexity of the approximator only depends on the complexity of the tests that you're trying to fool, not on the complexity of the object. So you can take any function of any degree, but if you want to approximate it against degree d tests, your approximator will be degree d. Right? So the complexity of the approximator this is like a slightly meta observation is related to the complexity of the test that you're trying to fool, not the object that you're trying to approximate.
Question? Prasad?
Yeah. Yes. Oh, sorry. Yeah.
So I was going to ask if capital N is going to depend on T, little t.
Yes. Capital N. This. The number of tests. Let's assume that we have like a sequence of tests, possibly infinite number of tests. Okay, we have a sequence of possibly infinite number of tests that we care about, and we have a function f, and like the one thing that's true is that in many situations, in complexity theory, this happens quite often, that when you're trying to approximate an object, the complexity of the approximator actually depends on the complexity of the test that you're trying to fool, rather than the complexity of the object itself. This is very obvious if I say di is all low degree functions. Suppose I say di is all low degree functions. Now f could be arbitrary degree, right? What would you do for, and I didn't care that f tilde is a density, right? You just project f to the span of the low degree functions. It will preserve the inner products with low degree functions. And so you give me any function, I'll just project it onto degree d span. That will be the approximator. You see that the degree of the approximator depends on the degree of the test, not on the original function. Okay, and so this is what's going to be very useful for us. So let me just state what we can prove here and see how and show you how we can prove it. So in this case we want a density. But this is the theorem that we can prove. There exists an approximator f tilde which is a density such that for every test function, for every di in D, di in a product f is within plus or minus eta of di in a product f tilde.
So Prasad, so di's don't need to be bounded in infinite?
Yes, yeah. So it we'll get there. Yes. So as I said, the complexity of f tilde depends on the complexity of di's, and the complexity of di's is what. So f tilde is not more complicated than the test in the following sense. F tilde is of the form you take a bunch of di's, you add them up, possibly with coefficients, and then you raise it to the exponential. Okay, so that's f tilde looks like that. It's exponential of a bunch of sum of a bunch of di's. how many of the di's are you going to add? You're going to add at most I need to use capital T. T log, sorry, T times the infinity norm of d divided by epsilon squared. I should say max infinity norm, but essentially infinity norm to all di's. So the function looks like a normalization factor times an exponential of a bunch of di's, exponential sum of a bunch of di's, and the number of di's you use is this much. Yeah.
So where does the approximation error come in?
Oh, sorry, I'm making mistakes. Sorry. Thanks. Yeah, this is eta squared. Well, okay, so let's see. So firstly, it does depend on f in the sense that it depends on the entropy of the min entropy of f, but just that, but nothing else. In particular, f could be a crazy function, whereas this is a very nice function. So let's see why this is nice before we go to the proof of this. So imagine. Actually, let me add a page. Okay, so imagine f, so here's a corollary, right? So if your tests were juntas, let's say di's are m juntas for some m, okay, they depend on a small number of variables. What can you say about the approximator, right? Let's say you have all m juntas, okay, every possible m junta, there are exponentially many of them. You would imagine that the approximator also depends on every variable. But actually, no, the approximator only depends on is t, the infinity norm of d by eta squared times m junta. Right? Because you just added a small number of di's, right? The way I think of it, I think of capital T as a small number of di's because you have a sufficiently high entropy distribution f. The T is really small, and so you're adding just a small number of di's, and you have this approximator which looks like an exponential of a small number of di's, but already it's sort of a very nice junta, but it's an approximation for f, which was not at all a junta, which is an arbitrary function.
So this doesn't depend on f at all?
T is just the
only on T, only on the board in which
yeah.
you're putting.
Yes.
It's approximating every function on that board.
Yes. Oh no. Well, the approximator f tilde depends on f. All I'm saying is that the complexity of the approximator, meaning in this case.
There are coefficients on the di's, right?
In the formula you've run.
There are coefficients on the di's. Sorry.
Okay.
Yeah.
Okay, good.
Yeah. So of course, sorry, the approximator depends on the f, right? You're trying to approximate. But what I was trying to say, the complexity of how complicated you think the approximator is doesn't depend on how complicated f is. F could be a very complicated function, but the approximator is going to be very simple because you're trying to fool a set of simple tests, and that's what happened here. So if you're trying to fool only juntas, then your approximator is going to be a junta. Yes.
Is there a scaling with the if you scale all of your d's by some factor c and eta by the same factor? Shouldn't the dependency on the infinite norm of d squared?
Yes. Sorry. Yeah. Thanks. Okay, so this is a, yes.
Are you going to say something about how this fits into the sort of lower bound?
Yeah, of course. Yes, yes. Yeah. So we'll just use this as in the lower bound, and we will use this results. But I just wanted to show this thing first because it's sort of the main conceptual thing which I learned from this paper. And so another fact which is also true is if each di, right, is if the, let's say di is a low degree polynomial, if degree of di is, let's say, d, okay, then what happens to the degree? How does f tilde look like? F tilde looks like this thing, right? It looks like this exponential in I think I should put an eta there, but it looks like an exponential in the sum of them, right? So you can do Taylor series expansion on this. You can expand this in Taylor series and truncate. So you could, right, you could take f tilde of x, and then you could expand e to the minus x in terms of Taylor series. E to the z is 1 plus z squared over 2 factorial and so on. And then you can truncate it. So you can get a low degree approximation for f tilde, right? You can truncate f tilde to get a low degree polynomial. And in particular, f tilde you can get is close to degree, d times whatever this quantity was, t times norm d infinity squared m by eta squared, close to square of a degree this polynomial.
Sorry, what is m here?
Where is m? Oh, sorry, it's d. Okay. Did I use d two times? Yeah, so I should just have d once. Okay, sorry, yeah. But we are not going to see why this, or it won't be too important what the actual number is here. It's just that you take di, which is a degree d polynomial, substitute here, expand out, you truncate the Taylor series at you get to truncate it at a certain degree, and then you get a low degree approximation. But low degree approximations were not so interesting as we saw earlier. But what you actually can get is a square of a low degree polynomial. The reason is because instead of, I can write f tilde as e to the something, I can write it as e to the, so f tilde is e to the z, so I can write it as e to the z over 2 whole squared. And then I can approximate e to the z over 2. I can truncate inside the square. So I get a square of a low degree polynomial this way. Right? So I'm able to approximate density by a square of a low degree polynomial as long as all I care about are tests which are low degree.
Okay.
Yeah.
Is there a relation between epsilon and eta?
Yeah, I think all my yeah. So, yeah. Sorry. You can pick the same eta and then you get the same in this sense. Yeah. Any other question? So yes.
So is this exactly the maximum entropy?
Yes, this is exactly the. So how do you get this? So let's see how you get this theorem. So you could do it in a couple of ways. One way to do it is to say the. So the way I like to do it is to sort of do it algorithmically. You could construct this approximation algorithmically using multiplicative weights or mirror descent. Okay. So what do? So I want to approximate this function f. Okay. So you start with an approximation, right? Here's the algorithm, right? You say, okay, let's initialize like f tilde to be the constant function. So you start with the uniform distribution as your approximation. So that's like the center of the simplex. So this is the 2 to the n dimensional simplex, which contains all densities on 0, 1 to the n. And then what I'm doing is I start with the center of the simplex, which is just the uniform distribution on 0, 1 to the n. Okay, and at any point in time, what you do is you see if you actually fool all the tests. right? You see if there exists some test that you didn't fool. Right? If there exists a test di such that f in a product d I is is very different from f tilde in a product di. So let's say it's greater or lesser than, let's say it's much greater than f in a product di plus eta. Okay. Or the other way around. The point is you find a test that you don't fool. When you find a test that you don't fool, you update your distribution multiplicatively. You say my new f tilde is going to be my old f tilde times e to the minus e to the eta times di of x. Right? You use the test to update your distribution in a multiplicative fashion. This is just multiplicative weights update method or mirror descent method. I mean, in some sense, this is very much the same as gradient descent, except that we want to stay in the world of densities. Right? We want to have our approximator to be a density, and therefore you would want to move in the simplex. And in order to move in the simplex, this is the correct way to update. If you want to move in the simplex, that's the fastest way to move on the simplex. But yeah. So, and the key is that whenever you do this gradient descent update, you actually move closer to f in KL divergence. Okay, so at each step, what happens is the KL divergence to f, KL divergence to the distribution f of f tilde and f decreases by okay. So basically at each step your KL divergence decreases. So in some sense, basically all I'm saying is you're in this space, and each time you see that the function f tilde and f are different on a test, you update and you learn something new. You actually get closer to f because you now actually move in that direction. So therefore, but you can't go on for too long. The distance you can go is exactly the KL divergence from f to your original point, which is uniform distribution, which we assumed is at most t. The KL divergence between uniform distribution and f was at most t. So that's the reason why you stop where you converge in t times the infinity norm of d by epsilon squared steps. Any questions on this? An alternate way to sort of get at this is to say each of these constraints on the approximator is a linear constraint. So you have a linear program, and the linear program is feasible because you could just say f tilde is equal to f, and f is always a good approximator for f. But you want the simplest such approximator, so you solve the max entropy. You find the maximum entropy f tilde that satisfies these linear constraints. That's an alternate way to do it. If you do it algorithmically, the advantage is you actually know the number of updates you're going to make, and you can get the Junta theorem out of it. Yeah. Any questions on this? Okay, so this is one of the main ingredients we're going to use in our lower bound for the correlation polytope. Okay, and before I actually go to the correlation polytope, I want to say that there's an analogous thing for matrix valued functions. So what happened so far is that we had a probability distribution f, and we approximated it by an exponential. Instead of a probability distribution, imagine you have a function q, which is a Just maybe it lost charge again. So I don't know why this happened. Okay. So this shouldn't happen, but yeah, apparently. Okay, so let's see. So just to sort of let's see, tell you where the notation is. So instead of, you had a function f which was non-negative on the hypercube. This is a probability distribution. Instead, now what you have is a function that outputs PSD matrices on the hypercube. Right? It's a function that outputs a matrix which is always PSD. So Q is a function, it's a matrix valued function that outputs PSD matrices. And it's sort of normalized in the sense that expected trace of Q is identity, is 1. And then you have a bunch of tests, but now all the tests are matrix valued tests. So you have a matrix valued function di, which is also outputs an R cross R matrix. Right, and then the test is just you do this. This is a test, and what you want is your approximator should match the test within an error of eta. Okay, that's the same. It's the same setup, except that instead of numbers you're getting PSD matrices. That's the same thing. And you can run matrix multiplicative weights update, and you get an exponential approximation. Exponential Q tilde will have a form which looks like e exponent in minus di. And then you can do the thing that we said earlier. You can expand. You can expand the Taylor series of the exponential function to get a low degree square. So the final theorem is that you can actually find a low degree matrix valued function whose square approximates Q. Okay, so we are able to approximate an arbitrary PSD valued function by the square of a low degree matrix valued function. That's the idea. Yes.
Is there no dependence on the output dimension of your PSD matrices in the degree of the polynomial?
No, there is no dependence. Essentially because
the entity takes care of that, right?
Yeah, because I have the spectral norm of Q is 2 to the t and the expectation is 1. So it's So it's the very analogous thing when the matrix multiplicative weights update. You have a KL divergence, the quantum version of that, and you measure progress with respect to that, and it's very analogous. There's nothing very different that goes on here. And after you get the exponential, you truncate it by using Taylor series, and you have the same approximation. So, yes.
What's little d?
Little d. So if di is a sequence of degree d tests, right, then the degree of the polynomial R is going to be this. So you see that one thing I should add is that, of course, the degree of the complexity or the degree of your approximator actually is good in the sense that it doesn't depend too much on the original function Q, but it is still larger than the complexity of the test. You're trying to fool degree d functions, you're not going to get degree d tests, degree d approximator, but something slightly larger. Okay, so this is going to be the main ingredient. I think now we are sort of ready to do the proof, except when we try to prove lower bounds for general extended formulations, the first thing you have to deal with is, okay, so what is a general extended formulation? You have a slack matrix. I don't know why this has stopped working altogether. Okay, so this is really bad. Okay, it's fine. So let's. I'll try to use the board and use this as sort of a marker. So okay, so now what we're trying to do, we're trying to prove lower bounds for general extended formulations. Okay, so so we have you know, our original setup, right? You have, so this is the so you have a slack matrix that's written as a non-negative factorization, where, or a PSD factorization. If it's a non-negative factorization, P sub g and Q sub x are non-negative vectors of dimension R, and if it's a PSD factorization, they are PSD matrices of dimension R. Okay. The first thing that we want to prove that such a thing doesn't exist. The first thing that we need to worry about is how large are these numbers P sub g and Q sub x. Right? Can PSD factorizations and non-negative factorizations have arbitrarily large numbers? In fact, even if you want to do a counting argument, you need to know how large are the numbers involved here in a non-negative factorization. Note that the numbers in the slack matrix itself are bounded. Let's say we know the numbers, they're like 1 or something, less than 1. But we don't know anything about these numbers, P sub g and Q sub x. They could be arbitrarily large. And the key thing which we'll use is that you can actually rescale these factorizations so that the numbers are nice. So in the LP case, the rescaling is really easy. It was done earlier. But in the SDP case, the work by Briet, Dadush, Pokuta, and the one I state here is by Fawzi, Gouveia, Pareo, Robinson, and Thomas, gives you the right rescaling. So what does this theorem say? Suppose you have a matrix M which has a PSD factorization of rank R. Okay? And let's say the matrix M has small entries. It's bounded by 1. What can we say about the entries of these matrices P's and Q's? It says that if you take essentially the spectral norm of P and Q, it's at most R. So you never need to use very large numbers in this. And what does this bias? This biases the fact that now we can actually do some truncation and force the numbers to be small. Okay, force the numbers to be small, and it also means that we only worry about bounded functions throughout the rest of the talk. The functions that we care about, they're all bounded. And that will be useful in our approximation when we said that the numbers are bound by 2 to the t and so on. It was very important there. Okay, so now we are good shape. We can actually start looking at the proof. Okay. I don't think my pen has come back, so.
Slide the whiteboards and write, project onto the whiteboards.
Oh yeah, that's right. Oh, thanks. That's fantastic. Yeah. Oh, that's fantastic. Yeah. Okay, so here's our approach. Again, we will use lower bounds for Sharali-Adams or sum of squares. In the rest of the talk, I'll actually be sort of mixing up Sharali-Adams and sum of squares, mainly because the proofs are going to be very similar, and so I won't really. So, but you know, let's see, for concreteness, let's say Sharali-Adams. So you start with an integrality gap instance for Sharali-Adams, just like we did for the symmetric case. You have a integrality gap instance like a graph or something, like a small. So it gives you a function that's not the sum of non-negative juntas. Okay, and from that, so that's an instance of size m, right? So it's a fixed size instance. Think of this as an integrality gap instance on 1,000 vertices or something. Okay, and from that we actually construct a family of hard instances. Well, what are these? Well, it's just you have n vertices, you have n variables, right? x1 through xn, and you have a function that only depends on m variables. M is like 1,000 or something. So this family of hard functions literally just consists of planting this function on arbitrary subsets. So psi sub s of x is just you take phi of x sub s. Okay. For every subset you get one such function, and every one of these functions is a hard function for Shirley items, because just took the same function and planted it in different places. But it's going to be useful that we have all of these together. Okay. So okay, suppose the correlation polytope has a small extended formulation, let's say small linear programming formulation. So suppose then there is we saw that every extended formulation has a family of functions associated with it, which is, we called it F. Okay, there are R functions. So these are, let's say, non-negative functions on the hypercube. Okay. So you have a family of functions on the hypercube that can express everything. In particular, it can also express these hard instances. So what is true is that H is in the cone. H is in the cone of F, right? Cone generated by F. This is clearly true. Okay. Now the idea is going to be very simple. We are going to approximate. This is an additional advantage. I can keep going down. Maybe not. Yeah. Okay. So the idea is we are going to approximate each Fi by a junta, right? And then that will imply that H is in the cone of non-negative juntas, which is a contradiction. A contradiction because it consists of the H consists of Shirley-Adams gap instances. Okay, so that's the basic idea. If we just the whole point of the approximation theorem that we talked about is that a general linear program consists of a general family of functions, and what we'll do is we'll approximate this general family of functions by juntas. And so then if you can express H using the general family of functions, you can also express using juntas, and then you're in trouble. Okay. Okay. So the key notion here is how good should the approximation be? Now I realize the one disadvantage with this is that over here it gets erased when I go to the next page. It stays here. Okay, it's fine. Okay, so how good should this approximation be? So let's go back and look at our hard instances and just understand them a little bit more. So we have the cone of non-negative juntas. The cone of non-negative juntas, and phi is a hard instance for Shirley-Adams, so it sits outside the cone. Not just phi, but every possible psi sub s, all of them sit outside the cone. Okay, let's just fix a size. Look at psi sub s, it sits outside the cone. Okay, so what is this space? This is the space of all functions on the hypercube, and then you have this cone of non-negative juntas there, and this psi s lives outside the cone. Okay, what that means is there is a separator that separates the two, and the separator is going to be this some other function d sub s, such that if on this side the inner product with d sub s is less than minus epsilon, on this side the inner product with d sub s is more than 0. Okay. So there's a distinguisher that separates my Shirley-Adams gap from non-negative juntas. Now all I need is that my approximator fools this distinguisher. Right? If the approximator fools this distinguisher, then we are in good shape. But before we get ahead of ourselves, let me just, so if you look at this picture, there's one more thing, couple of things you need to observe, is that if you are separating from the cone of non-negative juntas, right, you have this distinguisher that separates them. D itself is a junta, in the sense that it depends on only m coordinates. This is sort of clear because our function psi depends on m coordinates, right? And so you're really talking about functions on m bits, some subset of m bits, but really some subset of m bits. And therefore, you're really not working on all functions on 0, 1 to the n. You can think of this as happening in the space of functions on 0, 1 to the s. And therefore, it's really, this distinguisher only depends on m coordinates. So a distinguisher is like a junta. And that was sort of, we're going to exploit that in the sense that our distinguishers, like our gap instances are local. Right? This only depends on m coordinates. Our distinguishers are also local. Right? They only depend on m coordinates. Okay? And the corresponding thing in SOS will be, our distinguisher will be low degree. D sub s is low degree in the, but please ignore this thing if it's too much now. Okay, so this is the thing. Okay, so now the claim is if okay, so if we take each of these functions fi, and if we approximate it by a d junta, let's say fi non-negative d juntas. Okay. So let's do it this way. Suppose the approximator fi tilde for fi is a d junta. Suppose we get a d junta that approximates fi. Okay. Then what do we know? Well, because it's an approximator, we know that on every distinguisher it has the same value. Right. That's of course, that's what this is, because it's an approximator. And then because this is a d junta, you know that d sub s is non-negative there. If you give it a junta, it gives you a positive number. So if you give d sub s a junta, this gives you a positive number. A d junta, it gives you a positive number. Okay. So what this shows is that it's showing that all the fi's live on this side of the hyperplane. Right? If you could approximate each fi by a d junta, then even the fi's live on this side of the hyperplane. Okay. So all the fi's live on this side of the hyperplane. Then of course the cone of fi's will not contain this. Okay. Yes.
So what should I think of epsilon as, isn't it? What big an epsilon can you get from the
Right. So this epsilon is something that you get from the original gap instance, right? So the original, this whole picture was for the original gap instance, where this is a gap instance of Shelley-Adams, so it's away from the cone of non-negative juntas. So since you start with a fixed gap instance, you can even assume it to be a constant, and in many cases you can just assume it to, or you assume it to be a constant. Yeah. Note the because we start with a fixed gap instance for Shelley-Adams. There's really a constant separation that we can use. Okay, so this is that would be the proof. If we got if each fi to be a d junta, we would be done. Each fi tilde to be a d junta, we would be done. But of course, this is too good to hope for, because we already saw that the complexity of the approximator is actually more complicated than the distinguisher. So what we get is actually that each fi tilde is, from the approximation theorem, we get that each fi tilde is a larger junta. Is some, it's something much larger. It's like m times t over eta squared. It's a much larger junta, but it's still a junta. Okay. Okay. So this is where we are going to use. So because it's a larger junta, this fact is no longer true. Right? This fact is no longer true, because d sub s only separates the cone of d juntas, and okay. But why is this not a problem? Well, it's not a problem because of the following reason. Imagine picking a subset S at random. Right? Like pick a random planting. So we have this picture, so S is picked at random. Okay. So Fi tilde is some junta, right? It's some junta which is, if this number looks complicated, think of it as like root n or something. Okay, something much smaller than n. Okay, so your so you constructed an approximator for each of the Fi's, which is like a root n junta. So each Fi now depends on a subset of size root n. It's a root n junta. Okay. That's what each Fi tilde does. But now what you do is you pick a subset S at random and you look at just phi sub s, psi sub s. Okay, consider psi sub s. Okay. Now, firstly, how many look at any fixed Fi, right? For a fixed Fi, fixed I, for a fixed I, look at Fi tilde, right? It depends on a subset of root n coordinates. How many of these coordinates fall inside the subset that you care about? Okay. Actually, what you expect is, this is a set of size m, this is a set of size root n or something, so it's like less than m over root n. The expected size is m over root n, and it's in fact concentrated. So this the probability that the size is, I could say the probability that the intersection size is more than t is like less than n to the minus, let's say 0.1 t. So so we approximate each Fi by a root n junta, but then now if I look at a random instance chosen here, restricted to these variables, these are much stronger juntas. You can apply union bound over all the functions and say that if you have only n to the t, if you have if there exists, if the size of the family is smaller than n to the 0.1 t, okay, then there's a good chance that all of them are d juntas. Let's say if I use d here, n to the 0.1 d, then restricted to the set that you chose, all Fi are d juntas. So this is where random restriction is showing up. This is like the random restriction step. All Fi tilde are d juntas. Yes, all Fi tilde are d juntas, restricted to that. And that means that when you do this calculation, you say d sub s into product Fi is equal to this. Okay, and then you say, oh, look at this inner product. What is this inner product really? This inner product is really expectation over x, d sub s of x, Fi tilde of x. Okay, right? And but d sub s only depends on x sub s. So I can average out the coordinates outside x sub s. So I can take away the dependence on Fi tilde on the remaining coordinates. So basically, all I'm saying is this is equal to inner product of d sub s times the expectation where you average out the outside coordinates. Okay, and so this is actually a junta which only depends on the intersecting coordinates, which is s intersection j, and it's a good junta. It's a d junta. Okay, so that's where random restriction shows up. Now, it seems like random restriction is very crucial here, and it's not just. I feel like it's not just crucial here. It's crucial in, I think, maybe half the proofs in complexity theory. That's what is going on. Half the lower bounds in complexity theory. Half the lower bounds in complexity theory. That's what is going on. That you really need random restriction. The same happens in proof complexity, in circuit complexity. It's really important that you have the symmetry. The key thing that we are using is the fact that the set of instances that we start with, which is the set of all graphs, has this symmetry. Even though the polytope doesn't have this symmetry, the set of graphs have the symmetry that I can plant my instance anywhere. I can make any subset of bits relevant. and this is sort of used in parity lower bound spaces 0 and everywhere. So the random restriction is not a trick that we could get away with here. The learning itself, maybe it's not very crucial. Maybe there are better ways to do it than to do learning. Okay, so
balance the parameters, you lose something because of this, I guess. So what is the bound you get for, say, the size if you don't for approximating max cut, say?
Yes. So the reason. Okay, so the one thing that you lose because of a random restriction is that you can never get exponential bounds. You can get at most 2 to the n to the 0.5 or something. That's already the case. But in this proof, we lose a lot more than that because the thing that I hid was the infinity norm of the ds, right? The infinity norm of the distinguisher. The infinity norm of the distinguisher, we didn't care about it because we started with a constant size gap instance. But if you want to get a good lower bound, you need to start with a large gap instance, and then the infinity norm of ds starts growing very quickly. So this particular proof only gives you lower bounds of up to size n to the log n. It doesn't give you better than n to the log n. But it gives you a strong theorem that among all LP relaxations of size n to the d, degree d sum of squares gives you the among all LP relaxations, the degree d Shirley-Adams gives the best approximation. Among all SDP relaxations, degree d sum of squares gives the best approximation for the roughly the same size. But this only works till n to the log n. In a newer work, we get exponential lower bounds, but that is it's a different.
A different approach, or you clean up the bounds on the ends?
No, it's a different approach. It uses communication complexity techniques. Ideas inspired from communication complexity, but I don't understand that proof well enough to see what
the high non-negative rank for the same.
Yes. You're still showing the same result for beyond n to the log n, still showing that among degree d relaxations, among relaxations of size n to the d, Shirley-Adams is the optimal. But the proof itself is, it has a bunch of, non-canonical, like not the first thing you do. This seems like most of the things you do are the first canonical things you would try. And I don't have to say anything about, I talked about the sum of LP lower bound here, but I don't think I have to say anything about the SDP lower bound because it's essentially the same.
You moved the boards away.
Yes. Yeah. There's not much to say about the SDP lower bound because they're essentially the same. And I guess I should state some open questions. Of course, one question is matching polytope. Does matching polytope have small size SDP extended formulations? Another question is if you just take max 3 sat, can you get better than 7/8 using sub-exponential size SDP formulations? That's the same question as push these results beyond n to the log n to 2 to the n for SDPs. We don't know how to do that.
So you're saying you can, in the new work you do it for LPs, but
not SDPs. Yeah. Any questions? I think I'll stop here.
Questions for Prasad?
So if you apply the same for matching, do you prove that you cannot get to the log n size?
The question was, can we do the same for matching? And no, we tried quite a bit. It didn't work because the Fourier analysis gets very messy on matchings. So the reason is, I guess we talk about degree d functions on matchings and so on. Right? If you take the space of functions on matching and break it up into different degrees, then it's where the projections onto low degree. You don't get the result because of I guess the one thing concretely that blows up is where you had the infinity norm of the distinguisher. You need a proof that the infinity norm of the distinguisher is small. If you just use the trivial bound on the infinity norm of the distinguisher, it's really large and so on.
The seed problem, the constant size problem, we don't know. Is that?
Yeah, so the even if you took a degree 3 matching lower bound, you look at it on n vertices, the infinity norm of distinguisher is n cube, I think, or it grows with n. I guess because one concrete issue is really the 0, 1 to the n has product structure. So I can really place a smaller instance inside a bigger instance. In matching, you can't really place a smaller instance anywhere because the edges have to leave out, right? Every vertex needs to be paired in every matching. So if you just place a small instance somewhere, in most of the matchings, all the edges will be leaving out. So it's yeah. So I don't know, what's the right way to do it. But yeah, you'd think that just by analyzing functions on matchings, you should be able to prove a lower bound.
Any other questions?
Do you think this can be extended to other stronger computational models? I mean, rather than explicit extended formulations? Somehow if you have an auxiliary cone and somehow that's not, I mean, that's tractable to compute somehow.
I could be. I mean, as long as we have all this convexity thing, these things might still work. It's really because we have convexity, you still have the duality, you still have the factorization theorems or something. Yeah, I could still possibly prove it. Yeah.
And you still need, like, to some extent, to be able to use rescaling things to get the size of them, and that's it's unclear what cones other than like SE. Like it has the components have a lot of symmetry.
Okay, any maybe final quick question? Not, let's thank Prasad and all this.